Hello everyone, welcome to our differential equation class. In this video we are going to talk about solutions to second order linear differential equations that are non-homogeneous. First we are going to generalize the general solution theorem we have proven for homogeneous equations. We are going to generalize that to non-homogeneous equations, and then we are going to introduce a method to find solutions to non-homogeneous equations, which is called undetermined coefficient, which is a fancy name for guessing the solution in the case that the non-homogeneous part of the equation is simple enough. And we are going to see how this works in a few examples. So that's the plan for today. Let's start with the general solution theorem that we have seen in a previous video. So recall we studied that theorem in the particular case that the equation is homogeneous. That is, we have an equation of the form L of y equals 0, where L of y is a linear operator, second order linear operator with constant coefficients. So in that case, we have a general solution theorem, and the theorem is this. If we have two functions, y1 and y2, which are solutions of the homogeneous equation L of y equals 0, L of y1 equals 0, L of y2 equals 0, so recall L is an operator of this form, and suppose that the functions y1 and y2 are not proportional to each other. We have a name for this type of functions, fundamental solutions. Then the general solution theorem says that all solutions of this equation, are linear combinations of the two fundamental solutions. In other words, to find all the solutions of the differential equation that is linear and homogeneous, you need to find only two solutions that they are not proportional to each other. And then you found all the solutions. So instead of finding all, you find two. The proof of this statement is based on linearity. So because the only thing we need to do is we need to compute what is L of C1 y1 of t plus C2 y2 of t. Well, linearity says that this is equal C1 L of y1 of t plus C2 L of y2 of t. But now we know that we use the equations. On y1 we know that this is 0 and this is 0. Therefore this is C1 times 0 plus C2 times 0. So it doesn't matter what C1 and C2 are, we get 0. So it's very easy to show, based on linearity, that these linear combinations are solutions of the equation. What is hard to show is, in this theorem, is that these are all the solutions. But it can be proven. But you need linearity to start proving this theorem. Now, this theorem is not going to work in the case of non-homogeneous equations. So this proof fails for non-homogeneous equations, and because what it fails is linearity. So even we cannot start the proof, because see what happens if we assume, suppose L1 is solution of a non-homogeneous equation like f, L1 of L of y1 is equal f, different from 0, and suppose that L of y2 is also solution of the same equation. Then what happens with the addition? Then, for example, what is L of y1 plus y2? Well, we still have linearity in the operator, but we don't have this over here is superposition. and this is what fails, superposition. Superposition means you have two solutions, then the linear combination is also a solution, and this is what is going to fail now. We still have linearity because the left hand side, the operator is the same, so this is equal to L of y1 plus L of y2, so linearity is okay, linearity. But now we have that the L of y1 is f and L of y2 is also f, and now we end up with 2f. So what we don't have now is superposition. Superposition fails. And that's why this formula for the general solution of homogeneous equation, this formula is not true for general solutions of non-homogeneous equations. So we need to generalize this theorem. And this is what we do now. What happens in the non-homogeneous case? Well, what is actually can be proven is the following statement. Suppose now that we have y1 and y2 which are not proportional to each other, and they are solutions of the homogeneous equation. So equals 0 here. Okay, this is y1 and y2, just like before. And now suppose somehow you find the function yp, which is solution of the non-homogeneous equation with an f here. The name p here stands for a particular solution of the non-homogeneous equation. Then one can prove that all the solutions of the non-homogeneous equation are given by the particular solution you found plus any linear combination of solutions of the homogeneous equation. So this is the new general solution theorem for non-homogeneous equations. Notice that to find all the solutions for the homogeneous equation equals 0 here, we needed to find two functions which we called fundamental solutions. Now, to find all solutions of the non-homogeneous equation, we need to find three functions, the same two that we had to find before, plus a new function that is what we called the particular solution of the non-homogeneous problem. So, how do we prove this statement? Well, the proof is not complicated if one realizes the following fact. First, let's suppose we have yp to be a particular solution of the non-homogeneous equation, and suppose you have a second solution of the same equation. Suppose y is also another solution of the same equation with the same f. So the proof is simple once we realize the following, that y of t minus the particular solution is solution of the homogeneous equation. Then we are going to prove that. What is L of the difference? L, the linear operator. Well, by linearity, we see that this has to be L acting on y of t minus L acting on yp of t. Okay, but we know that this here is equal f, because this is our assumption, solution of the non-homogeneous equation, and this is solution of the same non-homogeneous equation, so you have f minus f, which is actually equal 0. So it turns out that the difference of the two solutions of the non-homogeneous equation satisfies the homogeneous equation. So y of t minus yp of t solves the homogeneous equation. But we know all the solutions to the homogeneous equations. All the solutions. We know all the solutions. All the solutions of the homogeneous equation, which are linear combination of y1 and y2. So y of t minus yp of t has to be a linear combination of one fundamental solution of the homogeneous equation plus the other fundamental solution of the homogeneous equation. But this is actually the formula we wanted to show. So that's so simple is the proof. So as a summary of the general solution theorem for non-homogeneous equation, now we need to find three functions: solution of the homogeneous equation, fundamental solutions, then a particular solution of the non-homogeneous equation, and then we have all the solutions of the non-homogeneous equation. The rest of the video we are going to focus on how to find this particular solution. We know how to find the fundamental solutions of the homogeneous equation, so now we need to figure out a way to find the particular solution of the non-homogeneous equation. Once we have that, this formula gives us all the solutions. Maybe the simplest way to find this particular solution of the non-homogeneous problem is by guessing. In the same way we use guessing to get the fundamental solutions of the homogeneous equation. Guessing is gonna work if the right-hand side of the equation is simple enough. Let's see how this guessing method works in an example. By the way, the guessing method is called Undetermined Coefficients. And let's see how it works in this example. Find all solutions of this equation, and this is a non-homogeneous equation, second order linear constant coefficients. As usual, we are going to call this side of the equation the operator L of y, and the other side we are going to call it f of y, f of t. Okay, let's solve this problem. How we can find all the solutions? Well, we need to find, we know that the general solution of this problem, well, we have a formula for that, so we are going to use that formula from the previous theorem. It's an arbitrary linear combination of solutions y1 and y2, which are fundamental solutions of the homogeneous equation, plus a particular solution of the non-homogeneous problem. So with, let's say, just to be clear, with L of y1, 0, solution of the homogeneous equation, y2 is also solution of the homogeneous equation. They are not proportional to each other, and yp is solution, any solution we can find of the non-homogeneous problem. So let's start with the homogeneous equation. How do we find the solutions to that equation? Well, the homogeneous equation, recall, is L of y equals 0. We want to find a fundamental solution to that equation, so the equation is y double prime minus 4y prime plus 3y equals 0. We are solving the homogeneous equation. And what do? We guess. We get solutions of the form y of t equal exponential rt. Actually, let's put some coefficient exponential RT. In the previous video we chose this coefficient to be 1, but now we are going to see why we chose it to be 1. So let's put that into the equation, and what do we get? If we do the calculations, what we are going to get is we are going to pull common factor k, we are going to pull common factor exponential RT, and then we are going to have here r squared minus 4r plus 3, all that equals 0. And now you see why we chose this coefficient to be 1 before, because it doesn't play any role in solving the equation, so we divide by that coefficient. And we also divide by the exponential, because this is equal 0, so the exponential is not going to play any role in solving this equation, only r is going to play a role. So the exponential goes away, and then we get the equation that we call the characteristic equation for the exponent, and that is going to determine what are the values of the exponential. And we use the formula. The formula here is r plus minus, so we solve for r, and then it's 1/2. Then we have positive 4 plus minus the square root of negative 4 squared, minus 4 times 3, minus 4 times 3. That is the formula for the roots. So we work this out a little bit, and we are going to get 1/2 4 plus minus the square root of 16 minus 12, which is 4. So we are going to end up with 1/2 4 plus minus square root of 4, which is 2. So we end up here with, let's put it here, r plus minus is, parenthesis, then it's going to be 2 plus minus 1, so we have two solutions, r plus, which is 3, and r minus, which is 1. So with that, we end up with the fundamental solutions y1, which is going to be, or we could call it y plus, but let's call it y1, which is k doesn't matter, so we put k equal 1, and then we have exponential 3t, and the other solution y2 is exponential t. And these are fundamental solutions, because they are not proportional to each other, fundamental solutions of the homogeneous equation. Okay, we obtained this part of the general solution. Now we need to guess yp, the non-homogeneous, the solution of the non-homogeneous equation. So now particular solution here. All right, so we need to find the yp solution of yp equal f, which is essentially this equation is yp double prime minus 4 yp prime plus 3 yp, we are looking for yp, equal 5 exponential 2t. And what we are going to do? Well, like before, we are going to guess a solution, and we are going to guess an exponential. So in this case, we have f of t is 5 exponential 2t. And now what we are going to do is we are going to guess something of the form like before, k exponential rt. Let's put that into the equation, and let's see what do we get. We compute the two derivatives as usual, so we need to do k exponential rt, compute two derivatives, then minus 4 k exponential rt first derivative plus 3 k exponential rt, and now this has to be equal to 5 exponential 2t. Okay, we compute the derivatives, and we can pull common factor after the derivatives are going to drop an r, 2r, so r squared, and then we can pull common factor k exponential rt, and we are going to have here r squared minus 4r plus 3, all common factor, and then this has to be 5 exponential 2t. And here is where we are right now. And notice that this polynomial in R that we have here is actually the characteristic polynomial P of R that we got in the homogeneous equation. It's exactly the same polynomial here. But now things are different, because now when I used to have 0 here, then I can divide by k and divide by the exponential, and it's still 0. But now we cannot divide by the exponential, because it's going to show up on this side. If we simplify the exponential, rt is going to show here now. And what we can do now, so now actually what we need to do is we need to choose r in a different way. We need to choose r so that this exponential cancels this exponential. So now what we need to do is we need to choose, let's say here, let's say choose r to be 2. We need to choose that, because if with that choice, what happens? Then what we are going to have is k exponential 2t. Now r is 2, so we are going to have 2 squared minus 4 times 2 plus 3. So the choice has some consequences all over the equation. And then here we have 5 exponential 2t. So now what we have here is actually the characteristic polynomial evaluated at 2. Okay, but now because of that choice, we can simplify the exponentials. And now notice that we need k. K before is simplified, but now k is going to be actually very important, because it's going to be determined by this 5 and whatever this number is. So now maybe it's a good idea to, let's see, I'm not sure, to put these two equations, yeah, one after below the other, nicer. So now what do we have? We have what is the end calculation here? Well, we have k, the characteristic polynomial at 2 has to be equal 5. So what is the characteristic polynomial at 2? Well, is what we have here, 4 minus 8 plus 3. So you see, we end up with minus 4 plus 3, so it's negative 1. So that is what k is. K, we found k. K is negative 5. So now we need k, because k is going to be fixed by the equation. So let me tell you where this comes from. It's super simple, but negative 1 equal 5. We multiply by negative 1 on both sides, and we get k is equal negative 5. That is where that came from. And that's it. Now we have our particular solution. Yp of t, we fix r and k is negative 5 exponential 2t. So that's how guessing works for the non-homogeneous case. So let's summarize what we just did. When we have for f of t equal some coefficient exponential 2t, we need to guess yp to be some coefficient that we find out later exponential the same the same coefficient, so the same exponent here. This is what we chose over here. And we did it so that these exponentials cancel out. Okay, and this the method is called undetermined coefficient because this is the undetermined coefficient. Undetermined coefficient. And then we have our general solution. General solution. The general solution then is y of t equal a constant exponential 3t, solution of the homogeneous equation, another constant, the other solution of the homogeneous equation, and then we have minus 5 exponential 2t. So that is how we find the general solution by guessing, or in a more fancy way, using the undetermined coefficient method. What happens if we have an initial value problem? Suppose we have the same equation with the same source, everything the same, but we need to find the solution of an initial value problem. Well, we find the general solution and then we use the initial conditions to get the constants. Now, the formula for the constants, we need to be careful because we have this extra term. So let's see how this is done. Solution is just a simple calculation. So first, find the general solution to solve an initial value problem. We already did, and this is y of t is, well, is right here. So let's copy this over because it's that equation. Okay, and now the initial conditions. The initial conditions involve the derivative, so let's compute the derivative right now. Y prime of t is going to be 3 c1 exponential 3t plus c2 exponential t, and now minus 10 exponential 2t. That should be the derivative. So notice now that in all the calculations we are going to have this term here. But that's the only difference with the previous cases. So now initial condition 1 is the function at 0, and now the function at 0 is c1 plus c2 minus 5. And then 2 is the derivative at 0, which is 3c1 plus c2 minus 10. So now we have the contribution from the particular solution in these equations, but that's about it. So from here we get that the equation we need to solve is we move the 5 to the other side, we move the 10 to the other side, and the equation we need to solve is c1 plus c2 is equal 6, and 3 c1 plus c2 is equal 12. So these are the equations to solve. And well, we can solve it in the usual way. For example, we can say, okay, c2 is 6 minus c1, and we put it here, so we have 3c1, c2 is 6 minus c1 equal 12. So that means that 2c1 is equal 6, which means c1 is 3. So that's how we solve it, and then that means that c2 then is 6 minus 3 is also 3. And that is the solution in this case. Y of t is going to be 3 exponential 3t plus 3 exponential t minus 5 exponential 2t. And that's how we solve non-homogeneous equations by guessing a particular solution and using the general solution formula. Now, this idea not always works, as we can see in the following example. We have exactly the same left-hand side, so over here is the same operator L from the previous example, but we changed the right-hand side. We kept the 5, we kept the exponential, but now we changed the exponent. Instead of 2, recall before we have exponential 2t, now we change it to exponential 3t. And that's enough to create some troubles solution. How do we solve this problem? Well, as before, we need to solve the homogeneous equation, which we did. So the homogeneous equation is L of y equals 0. That is the same equation in the previous problem. This is done. And we got r plus to be 3, r minus to be 1. And then the fundamental solutions are y1 of t equal exponential 3t and y2 of t, which was exponential t. So this is done from the previous problem. It's the same homogeneous equation. Okay, so now let's guess the particular solution. The particular solution. Well, we have an equation of the form L of y particular equal f, and the equation is very similar to the equation we had before, y particular double prime minus 4 y particular prime plus 3 y particular, and now is equal 5, but now is exponential 3t. Well, that's not a big problem, because our right hand side is f of t is 5 exponential 3t, and we learned that in the previous problem that we should guess the same exponential, so it cancels out later on in the calculation. So we should guess an undetermined coefficient exponential with the same exponent. So if we have here 3, we need to put here 3, so they cancel out later. Okay. But notice one little problem here, and that is that this function that we have here actually is a solution of the homogeneous equation, and that is going to create a problem. This is solution of the homogeneous equation. That is going to create a problem. Let's see what the problem is. Suppose we don't care that is solution of the homogeneous equation and we continue. What do we need to do? We need to compute k exponential 3t double prime minus 4 k exponential 3t prime plus 3 k exponential 3t, and all that has to be equal 5 exponential 3t. The exponential has to cancel because that's why we chose that exponential. We compute the derivatives, so what we get, we are going to get k exponential 3t, and over here we are going to get 3 squared, which is 9, minus 4 times 3 plus 3, all that equal 5 exponential 3t, and because we chose that exponential, that is going to cancel, which is what we wanted. But we have a little problem here, because this here is the characteristic polynomial evaluated at 3. But as we see, this is 9 minus 12 plus 3, so this is actually 0. So we ended up with an equation of the form, the exponentials cancel out, but we ended up with an equation of the form 5 equals 0, which is not true. So this is a contradiction. Well, the contradiction comes from? Well, the contradiction comes from assuming that this is a solution, because this is not a solution. So the problem is that yp, that we chose to be the solution of the form exponential 3t proportional to that, is not the solution. This is the wrong guess. That is what is happening here. So, and why do we get 0? Well, we get 0 here because that has to be 0 because we are guessing a solution for a non-homogeneous equation, which is actually solution of the homogeneous equation right here. It has to be 0 because this is one of the roots of the polynomial. So what do we do now? Well, more trial and error, but we are going to summarize it a little bit. Trial and error, we need to try different functions. People found out that a good second guess is yp, let's call it yp2 now, is multiplied by t, the first guess, exponential 3t. Actually, the idea of this guess comes from solving a homogeneous equation with a repeated root. It doesn't matter, but multiply by t your first guess. So another way to write this is that the second guess is t times the first guess. And well, we do all over again. So we need to put that function into this function now into the equation. So for that we are going to need two things, the first and second derivatives. So let's compute it here, yp2 prime, but now it's more complicated because we have to compute the derivative of the product. So product rule. So the k is going to be outside, we are going to derivate the t, so we are going to have exponential 3t plus k t, and now we derivate the exponential, so drops a 3, exponential 3t. And now one more derivative, second derivative of the guess function, so here is 3k exponential 3t, and now product rule, 3k exponential 3t. Now I'm derivating here, the first term comes the derivative from t, and then plus 3 and 3 is 9 k t exponential 3t. They look long and very complicated, but actually there is a nicer way to write this down. We pull common factor k and exponential 3t on the first derivative, and then we are going to get 1 plus 3t. And here we do the same, k exponential 3t. Notice that this term is, this term is the same as this term, so we have 6. So we have 6 and then plus 90. So a little bit shorter. So now we put everything into the differential equation. So we are going to have the second derivative. The second derivative is k exponential 3t, 6 plus 90. This is the second derivative, minus 4. Now comes the first derivative, which is k exponential 3t, 1 plus 3t. And now plus 3, the original function, which is k t exponential 3t. All that has to be equal 5 exponential 3t. So this is the equation now. That's the differential equation. And now we can pull common factor k exponential 3t, common factor on the left. And now we have 6 minus 90. Then recall this factor is going to multiply here and is going to multiply there. So we are going to have minus 4 minus 12 t. The exponential is already common factor, and then plus 3t. All that has to be equal 5 exponential 3t. The calculation is a little bit more complicated, but now we can simplify the exponentials, which is what we wanted, and now we want an equation for k. Notice that the equation for k is going to be k. Here we have two types of terms inside here. Those with t, those without t. So let's put them together. We are going to have 6 minus 4 plus t, that multiplies 9 minus 12 plus 3 equal 5. Notice that here again we have the characteristic polynomial evaluated at 3, which is 0. So the terms that are multiplied by t are going to disappear. So all these terms go away, and then we end up with an equation of the form k multiplied by 4 has to be 5. So that's it. We found our solution, 5/4. That is k. 5/4? Why 5/4? It's wrong, isn't it? Because last time I checked, 6 minus 4 is 2, not 4. So this is 2 here. So that here is a 2. Alright, so hopefully now it's correct. And here is our particular solution for this problem, which took a little bit more work, which is 5/2 t exponential 3t. So that is how we solve this problem. Sometimes the first guess works, sometimes we need to multiply our guess by t. Okay, after these two examples we have a rough idea of how this method works, guessing. So here is a little bit of a summary. Suppose we have to solve this problem, find the particular solution of a non-homogeneous linear differential equation of second order with constant coefficients. So the idea is we given the function f, we do a first guess, and the first guess is going to be something proportional to the original source, in the case that the source function f is simple, and simple means essentially 3 cases. This is the case we've been working in the examples. If the right hand side of the equation is an exponential, then you need to guess. So here k is given, the big K is given because it's on the f side, and then we propose the solution to be proportional to the same exponential. So these are the same, and we saw how it works. What happens if we have a different function f, for example, a power function? So suppose here we have something of the form 7t squared. Well, in that case, you see k is given, 7, and this is a 2. So what trial and error says is that you need to guess the whole polynomial starting with the same power. So if here we have a 7t squared, this here should be some coefficient k2 t squared plus some coefficient times t plus some coefficient k0, starting with the same power. If here we have power 7, then we need 7 terms here, all the way up to 0, 7 or 8. What happens, this method also works if we have here, for example, 2, oh, that is not good. If we have, for example, 2 cosine of 3t. Well, in that case, that should be something of this form. Well, b is 3, this is 2. Well, then we need to guess is both cosine of 3t and sine of 3t with different coefficients, and find for k1 and k2. So this frequency is the same in the source and the guess, and then we need to find the coefficient. But we need to put both, because sometimes only the cosine is going to work, sometimes both is going to work. That depends on what do you have on the left hand side. The same here for sine. If you have a 3 sine of 70, well, then you need to choose here 7, and you need to put both terms and need to find k1 and k2 in terms of all that. So this is you can put more complicated functions on the right hand side and still guess, but the more complicated the functions, the more complicated the guess, and at the end this method gets so complicated that it's better to solve this equation with a different method. So we are going to use this method only for simple right hand sides. But we have seen that sometimes this first guess is wrong, because this function here could be solution of the homogeneous equation. We saw an example where that happened. So our first guess actually was solution of the homogeneous equation. In that case, what did we do? Well, we show that multiplying by t the first guess worked. There is one more case we haven't discussed, and that's it, that this second guess sometimes could be solution of the homogeneous equation again. Well, if that happens, multiply by t one more time. So t squared times the first guess. And this is there are no other possibility, because for second order equation, this is the worst that can happen. Once you have your correct guess, you put your guess into the equation and you find the undetermined coefficients, the undetermined coefficient that were here. So this is the method. And again, it works. It works with simple right-hand sides. We end this video with one last example, just to try a right-hand side that is different from exponentials. So what about if the right-hand side, so notice this left-hand side is exactly the same as before. I want to save time in computing solution of homogeneous equations. And now the right-hand side is a power function. This is f of t, is t squared. What do we do in this case? Solution. Well, we start with the homogeneous equation as usual. Homogeneous equation. We know the homogeneous equation is L of y equals 0, but this is already done. In the first example, we know that r plus is 3, r minus is 1. We know that the solution of the homogeneous equation are y1 of t equal exponential 3t and y2 of t exponential t. So we know all that. That's why I chose that left-hand side. We save some time. Now, the second part is, let's go to the particular solution. So f of t, so particular solution. And in this case, f of t is t squared. So that means that we should guess yp should be the whole polynomial that starts with power 2 until power 0. So it should be k2 t squared plus k1t plus k0. We put that into the equation, but to put that into the equation, we need to compute the derivatives. The derivatives are very simple because it's a polynomial. The first derivative is just 2 k2t plus k1, and then the second derivative is going to be a derivative on the first derivative, so it's going to be 2 k2. Very simple. So let's put everything into the equation, and starting with the second derivative. So we have second derivative, and the equation is right up here. There it is. So second derivative, that means let's put here 2 k2, that is the second derivative, minus 4 times the first derivative, which is 2 k2t plus k1, and then plus 3, the original function, which is the whole polynomial, k2 t squared, then plus k1t plus k0, and all that has to be equal t squared. So this is the equation, and this is an equation that has to be true, of course, for all t. So what do we do here? We reorder terms, a lot of terms. So for example, we are going to put all the terms that have t squared together. The terms that have t squared is, of course, this term here. Then this term that has a t squared is multiplied by k2, but it's also multiplied by 3. So these go together. Then we are going to put together the terms that have a t, so k1t, for example. Then t times k2 times 2, but it's also multiplied by the 4 and actually by the negative 4. And then the terms that don't have t, which is this term, that term multiplied by the negative 4, and this term multiplied by the 3. So let's emphasize that this has to be multiplied, and this has to be also multiplied. And the term with t here is actually also multiplied by the 3. Okay, so let's be careful. So what do we end up with? Term with t squared. Terms with t squared are going to be t squared that multiplies 1, but is 1 over here. But when we move it to the other side, it's negative 1. So negative 1, and then plus 3k2. Okay, then we have the terms that have a t, product t, which is going to be the 3k1. I started with these two terms, and then these two. So negative 8 k2. Okay, and then plus all the rest. All the rest is the term on the front, which is 2k2. Then minus 4k1. Recall, we need to multiply here. And then the last term is going to be plus 3k0. All that has to be equal 0 now, because recall, this term, we put it on the other side right here. Okay, but again, this is an equation that has to be true for all t. So we have a polynomial that has to be 0 for all t. It's a polynomial in t squared, in t, so up to t squared, which means that each coefficient that multiplies has to be 0. Multiply t has to be 0, because this is a polynomial of the form a t squared plus bt plus c equals 0. But this is we are not looking for the solutions for t. What we are saying, this equation, so we don't use the quadratic formula, because the quadratic formula gives us t. And here what we are saying is that something different. This equation is 0 for all t. In particular, at t equals 0, the solution also has to be true, which means that c has to be 0. But if c is 0, so you see there is an easy argument here that if you have an equation of the form a t squared plus bt plus c equals 0 for all t, that means that we can evaluate at 0 the equation, and we are going to get c, the coefficient c has to be 0. If this coefficient is 0, then the equation is actually a t squared plus bt equals 0, which means we can divide by t and end up with something of the form a t plus b has to be 0 for all t again. And now we can evaluate at 0 again, and that implies that b has to be 0, and if a and b are 0, that implies that a has to be 0. So this is a simple argument to show that each coefficient here, because this is an equation that has to hold for all t, this has to be 0, this has to be 0, and this has to be 0. Let's put this argument a little bit down here, and let's change it to something else. So because of this argument, each coefficient has to be 0, the coefficient that multiplies t, and then we have three equations. -1 plus 3k2 has to be 0, 3k1 minus 8k2 has to be 0, and 2k2 minus 4k1 plus 3k0 has to be 0. We start solving from the top, because the first equation says that k2 is 1/3. Now we put that 1/3 in the second equation, and we get that 3k1 minus 8/3 has to be 0, so k1 has to be 8/9. And now we put these 2 into the last equation, and now we have that 2/3 minus 4 times 8, 32, minus 32/9 plus 3k0 has to be 0. That is the last equation, so we put everything on the other side. 3k0 has to be equal. Now we have minus 6/9. See what I did? I multiply by 3 and by 3. Below is 9, on the top is 6. And then I move that to the other side, so negative. And then plus 32/9, which, by the way, this is 9, and then we have 30, and then we have 26. We divide by the 3, and we end up with k0, which is 26/27. And that's how we solve this problem from the top to the bottom, and all that implies that our particular solution to this problem is going to be 1/3 t squared plus 8/9 t plus 26/27. And yeah, that's how we solve for the particular solution when we have a power function on the right hand side. And that's it. This is a good place to stop. See you guys in the next video.